Hello and welcome to today's Regulator Basics Tech Talk presented by Swagelok Central Ontario and Atlantic Canada, one of more than 200 authorized Swagelok sales and service centers located around the world in 70 different countries. I'm Tim Phillips, Marketing Manager, and leading today's Tech Talk is our Training and Technical Support Manager, Phil Reid. Before we get started, a few housekeeping items. Please use the live event Q&A feature for all questions. Questions will be answered periodically throughout the session. If you have further questions after the completion of today's Tech Talk, please direct them to Phil Reid, whose email is on the screen, or the technical support team at your local Swagelok Sales and Service Center. We understand through extensive global research and firsthand experience that businesses are under pressure to do more with less, to maximize system performance while juggling smaller budgets, skilled labor gaps, and changing safety requirements. The COVID-19 pandemic only adds to these pressures. Swagelok and its sales and service centers, like Swagelok Central Ontario, Atlantic Canada, are here to lend a helping hand, to provide you with the right resources at the right time. Swagelok Central Ontario and Atlantic Canada has 3 locations: Mississauga, Ontario, Ottawa, Ontario, and St. John, New Brunswick. And we provide local engineering and technical support across central, eastern, and northern Ontario, as well as all of Atlantic Canada. We are one part of an extensive global network of Swagelok sales and service centers that are here to help you with your applications and share knowledge through our extensive training and system evaluation offering, much of which we are adapting to provide virtually to you. Whether you need help with an application or to improve your knowledge in a specific area, whatever your pressure, think of us as your solutions provider. Now I'd like to pass it over to our Training and Technical Support Manager, Phil Reid, to lead the Regulator Basics Tech Talk. Phil, take it away.
Thank you, Tim. My name's Phil Reid. I'm the Training and Technical Support Manager here at Swagelok Central Ontario and Atlantic Canada. We manage a team of field engineers. We provide training, fabrication, assembly services, and resources to support you. And joining me today, we're very fortunate to have Phil Daniels. Phil is a professional engineer here in the province of Ontario, and he's a mechanical solutions provider. Phil's formal education is in thermodynamics, specifically focusing on thermal fluids, 6 years with the Swagelok organization. And Phil is one of our technical support advisors in hose. Phil can perform audits and hose advisory, pressure regulator selection, and solutions, high pressure systems right up to 60,000 PSIG, and seal support systems, API 682 and various other seal plans. And Phil's dressed here in gear ready to go in and do an audit in a plant. So Phil will be helping and supporting and answering some of the questions as they come in today. We have a fairly large crowd and we like to share that. We put 2 Phils on this just so that we would confuse everybody right off the start. So today's Tech Talk is around regulator basics, and specifically today we want to, talk about the difference between a valve and a regulator. We want to understand some terminology around regulators because the speak is always the same. Differentiate components within the regulator and what their jobs are and how they contribute to performance, and then recognizing these performance attributes of various regulators. A little bit more specifically today, we realize there's a lot of different types of regulators, backfeed regulators, heated regulators, tank blanketing regulators, etc. So there are many types of regulators available, and go right up to 4-inch. So today's talk will be around the 2 most common regulators used today, and the first being a pressure reducing regulator, reducing pressure from a higher pressure to a lower pressure. And we'll talk about the performance criteria, some of the terms and definitions, and how this applies to selecting a regulator. We're going to look at back pressure regulators. Back pressure regulators A little bit different than a pressure reducing regulator. So we'll get into the basic theories of a back pressure regulator. We'll also talk about the terms and definitions and criteria and selecting. And then we'll take all of this and put it together and kind of come up with how we judge performance and the criteria that affects that and selecting a regulator. So we're going to start by talking a little bit about a valve and how a valve controls flow and a regulator controls pressure. So a valve, a manually operated valve like this, does not self-adjust to maintain flow. A pressure regulator will self-adjust to maintain a specific pressure. If we're looking at a higher pressure, reducing it down to a lower pressure, it's dynamically working all the time to maintain that pressure. So it provides a constant pressure so that an orifice can control flow. And if you have a regulating stem tip or a metering stem tip on the valve, you simply are extracting that stem or drawing that stem out of that and increasing that cross-sectional area of the orifice. So regulators control pressure, valves control flow, two separate jobs. So let's look at these two regulators we're going to talk about today. First, a pressure reducing regulator controls pressure by sensing outlet pressure, and they control their own downstream pressure. So here we have a high pressure source being supplied to a regulator to the inlet, going to the sensing chamber and providing that downstream pressure, constant downstream pressure to a process or experiment or instrumentation, if you will. What a back pressure regulator does is it controls pressure from the process and it controls upstream pressure. So similar to a relief valve, but is not a relief valve. As pressure builds in the process, this will open when the pressure is built and it controls upstream pressure. Okay, so a back pressure regulator and a pressure reducing regulator. Let's take a little closer look at a pressure reducing regulator and how they're constructed. First of all, we have a control knob or adjustment knob at the top. This can be a thumb wheel or knob. We have the stem, which has fine threads on it, fine pitch threads, so that you can get more accurate control. There will be a range spring. So if you have a regulator that is 0 to 100 psi or 0 to 500 psi, the bodies may be the same, but the range spring will change. That's the force applied to the sensing element. As we move on down and look at this, we have the body cap, we have the cap ring, and inside we have the convoluted diaphragm, which is the sensing mechanism. Behind that, there's a backer plate that if someone reversed these orifices, you wouldn't have a catastrophic failure and blow the diaphragm out. We'll talk a little more about these later. So we have an inlet, and on the inlet of these regulators, notice there's a, excuse me, there's a fine filter in here. When I say fine, it's 25 micron. Most regulators cannot tolerate particles because this is a very small space, and we'll talk a little more about that as well. So we put a filter in here to try and catch the fleas and ticks, if you will, and not the cats and dogs. Anyway, moving ahead, we have the body and the outlet. This is the sensing chamber. We have the poppet and the seat. Let's break this down a little bit more and take a look at what's going on. So in the top of the regulator, in a pressure reducing regulator, we have the loading element, we have the range spring, which is applying the force onto the sensing element. And then in the bottom of the regulator, we have the poppet and the seat, which are the control elements. And these are dynamically moving to allow pressure to bleed up into the sensing chamber. If we take a closer look at these parts in that control element, the poppet, we have a damper at the bottom, which helps with resonance or vibration of the poppet and prolongs life. It makes it more stable. There's a poppet spring. It provides a little bit of force to help close the poppet or seat the poppet into the seat. Keep in mind, a regulator is not a shutoff device. A regulator is unreliable to be used as a shutoff device. So the poppet seats into the seat, and then there's a retainer that holds this mechanism all together. below the sensing chamber. In the upper works, we have the loading element, we have the adjustment stem, spring button, which simply keeps alignment of the range spring. We have the stop plate that is there. As I mentioned, if we have a catastrophic failure, someone reversed the ports accidentally of the regulator, and we did not have this, we could have a catastrophic failure or blowout of the diaphragm. So taking a little closer look at the diaphragms, depending on the sensitivity, depending on the pressure, I should say, it will affect the sensitivity. So the diaphragms are in general used up to about 500 psig. And they have this backing plate that I mentioned. Now they have greater sensitivity, they're more flexible, and better compatibility since we have no elastomers in the wetted area of the regulator. This is a alloy X750 diaphragm, so it's a metal. In the piston sensing type, you must keep in mind that there will be an elastomer. This has to seal. But when you get into higher pressures, 500 psi and on up like to 15,000 psi and beyond, it is a piston sensing mechanism. So it's a little bit less sensitive, still very sensitive, but a little bit less sensitive. And keep in mind that we now have introduced elastomeric or elastomeric materials in here to seal that in the system. So again, a diaphragm below 500 psi typically, and a piston is used at higher pressures. So let's have a look at this animation. We can see what happens in here. As we tighten down the control range of this regulator, we can see the pressure rose, and it's putting a force on it. As that force pushes this poppet down away from the seat, it allows that pressure to bleed up into the sensing chamber and then go to the outlet. So taking a little closer look at what's happening in here, we have these forces, and we're trying to balance forces. So we have F1, which is the range spring force acting down on the diaphragm sensing mechanism. F2, we have this little poppet spring in here that's also used to help seat the poppet back into the when it's in the closed position. We have the outlet pressure forces acting on the diaphragm as well that have to be taken into consideration here. And we have our inlet pressure forces. So our force balance equation would look like this. F1 equals F2 plus F3 plus F4. So if we change anything in this equation, we're going to get a different output. So taking a little closer look at these, again, we're going to look at the high pressure side. And then as we start to tighten down or compress the range spring in the top of the regulator, pushing down, it pushes the seat, the poppet down away from the seat and allows a small opening into the low pressure side for pressure to bleed in. And then as it bleeds up past the poppet, it goes from a high pressure to a low pressure. This opening is about 2/10,000ths of an inch, or a fraction of a millimeter. So it's a very small opening. And if you recall what I mentioned in the beginning with respect to having a filter, and we'll see the effects of this a little bit later, but a very small particle in that very small area can have adverse effects on the performance of a regulator. So now, as the sensing and diaphragm balances the forces and the pressure forces, this is continually dynamically moving as things change in here, and it balances these forces to continually give you that output pressure. And that's sort of basically how a pressure reducing regulator works. And with that, Phil, do we have any questions at this point?
Yeah, thanks, Phil. One question here so far, and the question is, what is the piston rated for? So a good question. Phil mentioned that the typical sensing element styles are a diaphragm style, which could be metal in this case, or sometimes could be other elastomers, or a piston element. So the diaphragm, while more sensitive, does have a lower pressure rating, but for the piston, it can be up to 10,000 psi in most regulators at the high end. So the inlet rating of the regulator would be 10,000, as well as the piston itself. So well suited for the high pressures up to 10,000 psi.
Thank you, Phil. So now let's have a look at a back pressure regulator. And a back pressure regulator works a little differently, but we have a loading, we have a sensing element, we have a control element, very similar to a back pressure regulator. But in this example, we're going to notice that we do not have a poppet. There are poppet style back pressure regulators, and we actually manufacture those as well. But in this case, there is no poppet. So we have a spring force is set for the outlet pressure, or pardon me, the upstream pressure in this case. So we want to maintain a specific pressure, and we set that through the range spring. As we have this set, the seat is initially closed. So we can see that the diaphragm here is sealed down onto this elastomer. There's no poppet. So now the force of the spring is forcing the sensing element down to seal on the poppet. Then, if the pressure is less than the set pressure, this will remain closed. Now, once this pressure exceeds the set pressure, set by our spring and manually set by the adjustment knob, if it remains less than the set pressure, this will remain closed. If the inlet pressure exceeds the set pressure, the regulator will then open and allow the excess pressure to vent off through the outlet. So the upstream pressure is maintained by the amount that the seat is opened and the movement of this element. So called accumulation, and we'll look at that a little bit later. But as we increase pressure, this will open more, and so you will have an increase in the amount of pressure. So just having a look at these two, we look at our pressure reducing regulator here on the left and our back pressure regulator on the right. So if you notice a couple of things, is we're looking at the inlet going up through the poppet and then bleeding into the sensing chamber. In the back pressure regulator, the inlet goes into the sensing chamber and then senses, and if it increases, it will then lift the diaphragm off the seat and allow that pressure to vent out. So very similar to our pressure reducing regulator, we have these key elements, and the F1, force balance equation again, we have F1 being the spring force, so the loading force. The next force we have are these inlet pressure forces acting on the diaphragm, as mentioned, is this, and this is a convoluted diaphragm too, by the way, because that increases the surface area and has an effect on increasing sensitivity. Force equals area times pressure. So if we increase that surface area, we have a greater sensitivity. And then we have the outlet pressure forces. When they're present, these must be lower than the inlet pressure force, obviously, because otherwise it would start to raise the diaphragm and allow it to bleed in the opposite direction. So again, these go together and it looks like F1 equals F2 plus F3. And as we apply the load, as we mentioned, the force down onto the element, it's being sensed, and then we have these balancing of forces. So we have the regulator with the inlet, and pardon me, as this compresses this spring, it's held down onto the elastomer that seals it up, and here we have pressure present in the sensing chamber. Now that pressure has overcome the force of the spring and allowed pressure to, if you will, called bleed off through the outlet. Phil, do we have any questions on back pressure regulators at this point?
Thanks, Phil. Yeah, we have one question here of when would you use a back pressure regulator versus a relief valve? So great question. Functionally, they are both very similar. They have a sensing element and then they lift to sort of bleed off pressure, but it's more about the application and where they should be used. So a back pressure regulator is intended to be a more sensitive device and used in a regular process. So it should normally open and modulate to set a certain process pressure. So for example, it may be set at 100 psi if you want to maintain a process at 100 and not any higher. So if pressure does build up, it will bleed off and slowly open to relieve that excess pressure. whereas a relief valve is more of a safety device. So again, it does sense that pressure and relieve when there's overpressure, but it would be above the normal working pressure. So for example, the process would be 100 psi. The relief valve may be set at 120 psi. So if there is that overpressure event, it can bleed off and relieve that excess pressure. Now it's important to note there's certain situations where there's an ASME safety code relief device required. So that is a special consideration. And of course, back pressure regulators should not be used in that application.
Thank you, Phil. Great explanation. That's a great question. We often get asked about relief valves and back pressure regulators. Thank you. So let's move ahead. We're going to have a look at some of the terms and definitions, around pressure regulators. So regardless of the particular make, brand, manufacturer, these are the common terms used across the industry, and they are present with everybody's regulators, pressure reducing regulators, back pressure regulators, etc. So these characteristics are typically exhibited in several common characteristics right across the industry. So let's start off with looking at droop or flow effect. Creep, accumulation, this is in a back pressure regulator, and we'll take a deeper dive into each of these in a sec. Choked flow, lock up or seat load drop, so lock up in a going from a flowing to a non-flowing condition, or seat load drop is when you're going from a non-flowing to a flowing condition. The Joule-Thomson effect, we'll look at the optimal flow range, and then something else that people often run into is supply pressure effect and wonder what's happening. So again, regardless who the manufacturer is or the type of regulator, it will exhibit these characteristics. And these are used when you're looking at flow curves. And the flow curves are absolutely the best way to select a regulator. So the CV of a regulator is measured when it's in the fully open position, and most regulators do not function in the fully open position. So in practice, the C sub V of a regulator is variable as it throttles. Remember, it's in a dynamic situation, so this is moving and it's basically throttling. So the flow curves in the catalog provide the best means of determining the CV, as these are based on actual flow data. So all the curves that we provide, and Phil Daniels, and we have a couple other regulator specialists, can provide you with help when selecting a regulator, get you to an optimal flow range that's going to give you the optimum performance. So flow curves are the best. If you're sizing using the C sub V, keep in mind that that CV is at the fully open position, and we'll take a look at a flow curve. So the best method is to use a flow curve. So how do we read these curves? Well, first of all, we want to look at what control range we're operating in. So we see the blue curves are a 0 to 250 psi flow range. So obviously we will not see this curve above 250. And these are the blue lines on here. The next thing we'll want to know is what our outlet pressures, inlet pressure is going to be. Our control range is 0 to 250, which is our outlet. Our inlet pressure in this case is selected at 500, so it will be the J curve. And if we were selecting in the 0 to 500, the J curve is here. So now we want to have a look at what other criteria is on here. We've already determined we're 0 to 250. We got a 500 psi inlet, so we know we're looking at the J curves. So on the vertical axis, we see the outlet pressure. Along the left-hand side, we see this is PSIG, and along the right-hand side, our outlet pressure in bar. Now along the X or horizontal axis, we will see the flow. So this is in standard cubic feet per minute along the bottom of nitrogen, and along the top we're looking at standard liters per minute of nitrogen. So outlet pressure and flow are dependent on each other, and we can see the characteristic of the flow curve. So let's take a little closer look at what we're talking about. So the first one is droop or flow effect. As if we've set the regulator static, in a static condition here at about 22 psig, what happens as soon as we start to flow, we get what is called seat load drop. So it drops, and then we start into a flowing condition. So droop is the reduction in outlet pressure experienced by pressure reducing regulators as the flow increases. So this curve is known as droop. So as this droop starts to flow increases, a flow effect, you start to experience droop on the flow curve. So now looking at this, we can determine where our optimum flow range would be. So let's take a little closer look at droop. We've set our regulator, as we mentioned here, static at the 22 psig, but now we've increased flow. We now have more flow required downstream to around 2 liters per minute. As we increase up to 4 standard cubic feet per minute, we drop down below 15 psi. As we increase out to around 6, we're down probably to 12 or 13 psig. So we haven't adjusted the regulator. All we've done is we've increased the flow demand downstream. So now we're starting to have an effect on the regulator, and that is the droop of the curve. If we go on down, looks like around 9 psig in our outlet pressure at 8 standard cubic feet per minute. So taking a look at these flow curves, you will be able to determine, with the other information we're going to talk about in a minute, if the regulator is suitable for your optimum flow and pressure range. Another thing that's very important is creep. And what creep is an increase in outlet pressure over time. I did mention earlier that a regulator is not a shutoff device, and a very, very small gap when the poppet drops away from the seat, we're in that 2/10,000ths of an inch range for the pressure to bleed through. So you can imagine if a small particle, for example, got lodged in there and held this regulator open, we're going to start to experience creep. And it's if the poppet does not fully seat in the orifice, and this can be caused by contamination, and this bleed through can equalize over time. So over time, the leakage can increase to a point where it's equal to the inlet pressure. So some of the causes of creep, number one is contamination. So something to keep in mind when you're setting up your system, if it's off a cylinder, for example, you get a certificate saying that the gas in the cylinder is 99.99% pure, but you do not receive anything that gives you any indication how old that cylinder is, where it's been, so you can start to there can be rust or different contaminations inside the cylinder. So this can damage the poppet, the seat. Misalignment of the poppet can also happen. And these are actual photographs of particles deposited onto that little tiny seat. And as I said, when we talk about this opening up about 2/10,000ths of an inch, a very small particle would keep that open and allow it to continue to bleed. Keep in mind, and I'll repeat it probably 3 more times, a regulator is not a shutoff device. So why is creep dangerous? If you have a 3000 psi, arbitrary here, but a 3000 psig source, and you are dropping it down to 100 psig, and that's the downstream is designed for this lower pressure. If we had this high pressure and this valve got shut off and we're experiencing creep in this regulator, we could have some catastrophic effects downstream. So what are some of the things we might be able to do? Well, filtration, as I mentioned, is very important. We can filter the fluid to minimize the damage to the regulator. So we added a filter here before the regulator. A relief valve to protect from the failure if creep does occur. We've added a relief valve on the downstream side. And as Phil mentioned earlier, ASME code may be required for an actual safety device. And if possible, always add a shutoff upstream of the regulator so that we can shut it off. We're not relying on that regulator as a shutoff device. Here I go again, but a regulator is not a shutoff device. Next one is accumulation. Accumulation relates to a back pressure regulator. And as we discussed Droop earlier for pressure reducing regulators, that effect in a back pressure regulator is known as accumulation. So as the flow from upstream increases, the set point pressure increases. Like Droop, this effect is most caused by the spring load, and then it's known as accumulation. So if we have this set at somewhere around 150 psig and we're experiencing this overpressure, it's starting to bleed some off in the flow, as that pressure increases, the flow increases, and so that is known as accumulation, the amount or volume of flow that is allowed to get through that regulator. So we're going to look at choked flow. And choked flow is when a regulator is no longer able to act as a pressure reducing regulator. It's simply acting as an orifice in this case, actually, because we're out at the end of the flow curves here, and there's absolutely no control after we get out to this end where we're dealing with choked flow. And that is exactly where that CV is taken that we assign to the regulators when the regulator is in the fully open position. So, you know, by increasing the actuation and the spring load will not increase the pressure or flow once you've come to a choked flow position. So lockup. The difference between a flowing and a non-flowing regulator. So when flow is stopped, we're starting to back off the regulator flow, or pardon me, the flow is starting to be reduced, and we start to come back on the flow curves as we reduce flow downstream demand. And then the balancing of forces, once we get back here, we'll put the regulator into what's called lockup, and that's at about 20, this is below 20 psi, and we may have set this regulator at about 22. So when it goes back to a static condition, you'll be reading about 22 psig on the actual regulator. So if we shut this valve off, we're going to see an increase in downstream pressure, and this is known as lockup. Now, I also mentioned if we start in this position and we start to a flow condition, this is then known as seat load drop. So going from a flowing to a non-flowing condition is lockup. Going from a non-flowing to a flowing condition is known as seat load drop. Joule-Thomson effect. I'm not sure if any of you have ever walked in and seen a regulator sweating profusely or frosted up, similar to the one we're looking at in this on this slide. But the temperature of a high pressure gas can drop considerably when there's a pressure drop. So if remember, we're putting it through that very small gap that we talked about. So we're experiencing a very large pressure drop. And just an example, with natural gas, the average temperature drop will be approximately 1 degree C for every 2 bar, or approximately 30 psi. And now how can we compensate for this? Well, we can heat the gas. We can put heat tracing on. We could use a vaporizing regulator, or we could add stages to the regulator. We could have 1, 2, or 3 regulators, so our pressure reduction is much smaller as we move to achieve the actual set point we're really looking for. So there are various types of regulators to address this. So let's take a look at some of this information on a flow curve now. We want to look at where the optimal flow range is. We want to avoid the choked flow area. We know that we have lockup and seat load drop in this region. So the portion of the flow curve which the regulator has its best performance is known as, is known as the optimal flow range. And here we see in this regulator, this is the flattest part of the curve. So we want to stay within this range, and this would be the operating range that we would look for the best performance out of this regulator. So a pressure regulator works best when you have a large differential pressure. So going from a very high inlet to a low outlet, and it really achieves its job in the balancing of forces when you have these high inlet pressures, lower outlet pressures. So a regulator should be used in the upper region. So if you're looking for a regulator and you're trying to control 90 psig, you'd want to use a 0 to 100 regulator, not a 0 to 250. You have great performance and great resolution in the upper end of the performance range. So again, you want to have try and have a larger pressure differential. So the optimal flow range is the portion of the flow curve that we talked about that we should operate in. So if we look at this example, we've set our regulator at 22 psig in the point of lockup. We've now found on our flow curve the 160 standard liters per minute. And so now we can assume that our regulator will now read on the pressure gauge about 13 psig as we have remained static. We have not changed the setting. So from the set point of 22 psig, as we start to flow out here to around 160 standard liters per minute, we're now going to be flowing at about 13 psig. So the difference in the start point to the outlet pressure, 22 psi is our start point, and our flow now is 13 psig. That's known as droop, or in this case, we have droop of about 9 psi. So droop is important to take into consideration because we really want to avoid that lockup and choked flow regions, and we want to stay in that optimal flow range for the regulator. And Phil, do we have any questions at this point?
We do. Thanks, Phil. The first couple questions here are about droop. So how do you combat droop, and how can droop be reduced when you have changes in flow? So really good question. Phil mentioned a bit about what droop is and how it occurs. But as far as how to combat droop, I guess the initial choice, if you look at different styles of regulators, the primary thing you do is lengthen the spring. So we do have some other models that really have a longer spring, which allows that as pressure changes and flows change, it has less of an effect on the spring because the spring is so long. But beyond that, there's other styles such as dome-loaded regulators where you eliminate the spring altogether, as well as external feedback and using pilot regulators. So especially when you get into the larger process regulators up to 2, 3, or 4 inch, and then when you have higher flows and flows that are fluctuating, that's when you may want to look to going to a dome-loaded or external feedback where you are feeding back that pressure and you're really creating a more stable outlet flow, which you might not experience from a smaller spring in your regulator. Another question here is about if there is increased accumulation, will the repeating result in a lower pressure set than the original set pressure on a back pressure regulator, I'm assuming. Generally, you do get repeatable set pressures. When you look at back pressure regulators versus relief valves, one of the main differences is in that sensing element. So relief valve is often for higher pressures. You have a small surface area on a piston or a poppet. That's typically where you do have resistances that may change. But when you look at a back pressure regulator, which typically has a wide diaphragm, you can get very repeatable set pressures as pressure accumulates and then comes back to your normal pressure. And then final question here, what are the benefits of the convoluted diaphragm being constructed out of Inconel? So good question. Yeah, our standard material is Inconel when you look at swage lock regulators. Common materials out there is often stainless steel or sometimes elastomers. They each have their own place, but especially with Inconel, it allows you to have that compatibility in a variety of applications. And we do have those convolutions in using Inconel, which gives you a really long life. When you're going to have that cycling and that constant cycling of the diaphragm, it avoids some of the fatigue you might see in certain applications.
Thank you, Phil. Really great questions. So let's move on and take a look now at the last one, supply pressure effect, or otherwise known as inlet dependency. So if the inlet in a single stage are known as a line regulator, if the inlet pressure drops, the outlet pressure goes up. Or If the inlet pressure goes up, the outlet pressure drops. Again, keeping in mind the balancing of forces. So if the inlet pressure creates this force and on the poppet, and the higher the inlet pressure, the higher the force, obviously. So we look at our force balance equation, and we have the F1, F2, F3, F4, and this will affect the balance. So we want to take a closer look at this. If we had a single stage line regulator, for example, on a cylinder, and that cylinder started to decrease, the pressure started to decrease. I lost my point. There we go. The inlet pressure starts to drop, where our cylinder's starting to decay, and then we haven't changed anything or the setting in the regulator, so this spring force will overcome those other forces that we're balancing and open the poppet more and allow greater pressure to come through, so the outlet pressure goes up. And we'll take a closer look at this. So what happens when the outlet pressure decreases? Pardon me, if the upstream pressure decreases, then we have down, and F3, our outlet pressure, will go up. So let's take a closer look. If we look at printed or published catalog literature from various manufacturers, and this happens to be from ours, amazing, we have supply pressure effect stated, and it is stated as a percentage of the control range. So of the reduction. So if we look at the 0.06 flow coefficient up to 100 psig control range, our supply pressure effect is 1 in a single stage line regulator. If we now look at a 2-stage regulator, and we use that same flow coefficient, and we use the same up to 100 psig pressure control range, it's now 100 times better, 0.01%. Okay, what does that mean? And please keep in mind that I just chose these because 1 and 1 are kind of easy to work with. Keep in mind that this supply pressure effect can be greater or even less in certain cases. So just keep in mind to look at the supply pressure effect. So we see the single stage line regulator, or most commonly known as line regulators, has the 1% supply pressure effect. The KCY, or typically known as a cylinder regulator, 2-stage regulator, has a 0.01% supply pressure effect. So very often used on cylinders. And it compensates for that fluctuating inlet pressure. And it's a diaphragm sensing, and essentially what we have here are 2 KPRs machined into one body back to back. All right, let's have a look at this. So the KPR is a supply pressure effect of 1%. So if we drop, we've set our regulator to 50 psig outlet pressure. If we drop from 2,000 psi from our cylinder down to 1,000, our outlet pressure is going to increase by 1% of that. And as we look at the equation, 1% of 1,000 equals 10. We're going to see an outlet pressure increase of 10. So we're going from 50 up to 60 psig when we've had this 1,000 psi decay in our bottle. So now let's take a look at this regulator. So here we have 2 KPRs machined back to back, as I mentioned. We have our inlet pressure coming in, and this is factory set to 500 psig. So we have our inlet pressure coming in, going through the first stage, the sensing chamber, going through a flow path in the regulator to our second stage, which is where we control our outlet, and that is set by the user to 50 psig. So now let's have a look at the 2-stage regulator. We've got our inlet of 3,600 psig coming in to our regulator. It is providing 500 psig to our second stage. So now if we had a pressure drop of 2,000 psig, we went from 3,600 down to 1,600. So coming out of the first stage, we're going to see an increase. The increase will be 520 psi as our outlet now going to the second stage, and our second stage has received an increase in pressure of 520 psig. So if we have an increase in inlet pressure, outlet pressure is going to drop, but it's only going to drop by 0.2 psig. So you're not even going to see that on a gauge typically. If you had transducers in the system or highly sensitive equipment, you would see this. But again, having experienced the decrease in inlet pressure, you get an increase in that outlet pressure from the first stage of the regulator, and now we have this in the second stage, a very small drop in outlet pressure. So that helps control the fluctuating inlet pressures. Something else, last full item here, is venting options. And we often get asked about vents, and they can be somewhat confusing to people. So we're going to try and explain these. First of all, we have no self vent, no captured vent. So this regulator is a line regulator, very similar to the one we've been looking at all day long, inlet through the up past the poppet, through the seat sensing chamber, and no vent, so it just goes down. If you set this regulator static, you cannot reduce the pressure after it's been set in a non-flowing condition. You'll have to have a flowing condition or a downstream method of venting it. So the next one is a self-vent, but no captured vent. So inlet pressure comes into the sensing chamber, but now we see we have a hole through the diaphragm and the backer plate. We've also added a different style poppet. So this now has an elastomeric seal, very similar to the back pressure regulator, but this seals. So now if we had increased downstream pressure and it were to overcome the force applied by the spring, that pressure would then vent out through this hole in the diaphragm and up into the body cap. But there's no captured vent, so there's always this little hole under the handle, even when there's no vent. So it will bleed out under the hole. So if you had very benign or inert media, definitely not liquids, but if you had, this would be a method of venting it. So now I can control my downstream pressure in a static condition because I can vent off that excess pressure. The next one we're going to look at is no self-vent, but it has a captured vent. So now we no longer see the hole up through the body cap. We now see either you could have a weldment here, or typically it's a 1/8 female NPT connection. And also you'll see there's an elastomer on the stem to help provide sealing of the stem, so that if we had a catastrophic failure, where this might be used is if you had a catastrophic failure of the diaphragm and it were a hazardous media, you might want to have a sniffer tube in the bonnet so that it would detect any leakage across that through that diaphragm. Also, it would help keep it from passing out past the stem. As you'll notice in these two examples, there's no seal on the stem. And in our last example, we have a self-vent and a captured vent. So now we have the vent up through the diaphragm. We have a captured vent and no hole out under the top. We have the elastomer on the stem to seal. And so if we're flowing in this condition and we are at a higher pressure on the downstream and we now want to back it off a little bit and reduce that pressure can be vented through this vent hole through the backer plate and the diaphragm, and then can be captured. So if you have any, again, hazardous medias, if it's liquids, you'd want to control it. If it's a liquid service, you would remove, just note to self, you would remove the little gauze 25 micron filter element that I talked about on the inlet if you're using these regulators in a liquid service. So the 4 types of venting: no self vent, no captured; self-vent, no captured vent, so we're allowed to vent and up through the handle, under the handle. No self-vent, but it's captured, so we're not venting anything, but we have a captured vent in case we have a catastrophic failure and we want to be able to detect it, sound an alarm, or shut something off. And then the self-vent, captured vent. So a few things we really want to talk about, and I heard Phil mention a couple of these in answering some of the questions, but today we covered pressure reducing and back pressure regulators. So if you were looking at trying to control, as Phil discussed, dome-loaded regulators, differential pressure regulators, cylinder changeover regulators, could have vaporizing or heated regulators. So we have a very wide range of regulators depending on the application, and some of our application solution engineers like Phil could certainly work with you to determine the functionality of what you're trying to do. We need to know the inlet pressure matched to the maximum supply pressure. If you have a 3000 psi inlet, you want to purchase a regulator that's capable of a 3000 or above supply pressure. And this will help determine the models, and it'll sometimes drive you to a different model, or you may have different seat materials, or it could be the choices of sensing elements. You want to know what the pressure control range is, matched to the maximum outlet pressure. And as I mentioned, try to stay as close to the high end of that. And this will also determine whether you're using a diaphragm sensing regulator or a piston sensing regulator. Flow requirements, as I mentioned, use the flow curves, call Phil Daniels, call Andrew Wright, call me. We'll certainly help you out. Calculations. You want to take into account supply pressure effect on the regulator. System compatibilities, again, materials of construction, seat materials, the diaphragms, are there elastomeric materials such as O-rings in the regulator? System functionality, again, will help determine, some of the things like venting options and other accessories, certificates for material test reports, etc. And then the various ancillary products, end connections, porting, hoses, mounting, gauges, and the list goes on. So a few things you really need to know: inlet pressure, outlet pressure, flow range, and the medium you're working with. Really nice and helpful to have is your temperature range, the loading mechanism, type bend connections that you're going to be looking at, and then the materials that are compatible with your system. And then it gets on into surface finishes, lubrication, certifications, material testing, and other detailed special requirements. So at this point, do we have any further questions, Phil?
Yeah, thanks, Phil. A lot of great questions today. Start here on the questions about supply pressure effect. So the first one here, after supply pressure effect, does it restabilize? Well, it would restabilize once the inlet pressure is, corrected, you could say. So for example, it usually occurs when you have a reduction in inlet pressure. So let's say you have a bottle that's at 3000 psi, and then it slowly empties and the inlet pressure reduces to 1000. That's when you would experience supply pressure effect. So when you replace the bottle, or your inlet pressure is then brought back to 3000 psi, the regulator would correct back to the original condition. Another question here, is supply pressure effect due to the reduced seat forces of the poppet on the seat causing passing through the seat? So good question. That's sort of a result of how, let's say, supply pressure effect is administered, by opening up the seat to allow pressure through, but realistically it's caused by the force balance, like Phil mentioned. So you have two forces from each of the springs, and then you have a force from the inlet pressure and the outlet pressure. So really, because the spring forces are constant, the only two things that can adjust to each other in this case is the inlet pressure and the outlet pressure. So because of that, when inlet pressure reduces, the outlet pressure has to increase in order to maintain that balance of forces. So yes, there is a bit of bleeding through, which creates that outlet pressure, but the reason the outlet pressure increases is due to that force balance. So good questions about supply pressure effect. Two more quick questions here. What type of regulators would you use for gas cylinders? So we talked about supply pressure effect, and that's really when it would be experienced is in those gas cylinders. So typically you would look at that two-stage regulator for gas cylinders. And final question we have here, do you provide tank blanketing regulators? So yes, we do. We talked about a variety of pressure reducing, back pressure, dual stage. Tank blanketing would be similar to these, but really they're much larger. You'd see a really wide diaphragm and extremely low set pressures that you would experience on tanks to make sure that you're protecting those tanks and filling that blanketing gas. Like Phil mentioned, this is regulator basics, but there's a wide variety of dome-loaded, as well as tank blanketing and many others that we could cover as well.
Thank you, Phil. Those are great questions today. So we have a team of field engineers and technical support, and regardless where you are in the world, there will be a Swagelok sales and service center located near you, and they will have a team similar to our team. And we have Andrew Wright, and Andrew has been with us over 10 years. And has a lot of field experience. We have Fozzie, Phil Daniels, who you've met here today on this call, Hassan, who is helping us out in the background today as well. Ali is looks after our applications and fabrication, and we have Chris Conrad out in the East Coast. And with that, Tim, I'm going to turn it over to you, and we can go from there.
Thanks, Phil. Wanted to thank everyone for attending today's Regulator Basics Tech Talk. We're always looking for feedback as we continue to roll out more and more Tech Talk webinars. You'll see on the Q&A live chat there is a link for our feedback survey, so feel free to click on that. You'll also see that in the slide you see on your screen as well. So any feedback you can offer will only help us improve. And coming up, some of our upcoming webinars, we have a webinar on mechanical seal support systems, webinar also coming up on the benefits of tube versus pipe, as well measurement devices introduction webinar and a hose basics webinar. And we'll be releasing dates in the near future for all of those, and we look forward to having you for those, answering your questions and helping you more with your applications. And just to let everyone know, the Q&A will be open for a few minutes after the live event. So if you have any other questions you wanted to fill in today, Phil Daniels will be able to respond to those. But thanks everyone for your time today. We appreciate it, and have a great day.